Hey guys, so in this video, I want to make this actually pretty quick. Just a review of the different types of superpositions that we have been dealing with in quantum mechanics. And I just realized I forgot a parentheses here, so we'll get to that. Um, so I have a table here. I've got our discrete superpositions and our continuous superpositions. And remember, as we saw in the last video, these can exist together. There are some quantities that are discrete, some quantities that are continuous, and we have to be able to do this superposition in a discrete basis or in a continuous basis. And so the we know how to do this superposition in both of these bases. I just want to recap this. So here we have psi being the sum over all values of j of c sub j, phi sub j, where we have some observable quantity q sub j, little q sub j, right? The probability of observing little q sub j is the norm squared, the absolute value squared of this coefficient c sub j. And so, in fact, you could show this expression is showing psi in the c sub j basis. P sub q sub p p sub q of j, or p of q sub j is the probability. Then we know this inner product. This is our orthonormality condition. Phi sub m inner product with phi sub n. Different states have to observe this orthonormality condition where this inner product is zero. It's like vectors. They're orthogonal. They're perpendicular. Right? That's how we know it's a good basis. Right? We've got our x, our y, our z-axis. Right? It's good that they're all perpendicular to each other. That allows for the that it just makes sense that it would be that way, and I believe I showed in section 2 why this is very important. And I showed in this section as well why this orthonormality condition gives us some really good results. In the continuous basis, we have the this wave function psi equaling the integral from negative infinity to infinity. Remember, adding up all the little possible values of this observable quantity q. And this c sub q we found has a lot of the times been actually expressing the function in the q basis. This is the thing. This right here is really what we're talking about when we're saying, in the q basis, it's this coefficient, right? And then this is the superposition. This is the wave function. But this coefficient tells us everything about so it's really the set of coefficients, this function, right? And so for any particular value of q, the c sub q norm squared gives us the probability density, right? And so we found, writing psi of x is really writing psi in the position basis, because for any value of x, its norm squared tells us about the probability density, and that's very important, right? That's what we're talking about when we're expressing it in a basis. We have it's like accessible information. When we write it like that, if I want to know, the probability of measuring q sub 3, all I have to do is look at it in this form, and hey, I found, c sub 3, and I figured that out. I take the norm squared. So if that makes sense, writing it in a basis is sort of like writing it in a form where this information is accessible, is very easily accessible. So when we wrote psi of x or psi tilde of k, right, then our probability density of having a wave vector k, or sorry, getting ahead of myself again, wave number k is this thing norm squared. And then the probabilities we know how to get from probability density to probability using an integral. And so we know that this inner product here, phi sub qm, inner product with phi sub qn, is delta, the Dirac delta of qm minus qn, and we've covered this all in another video. Notice when we're switching from discrete to continuous, and this is really the idea of the video, summations become integrals, probabilities become probability densities, Kronecker deltas become Dirac deltas. And that is generally how people will summarize going from a discrete basis to a continuous basis, right? We have sums turn to integrals, probabilities become probability densities, Dirac delta or Kronecker deltas become Dirac deltas, and often there's actually another one, but that's a little bit above where we are right now. Sometimes people also say that commutators become Gaussian brackets. So, but that is not anything you need to worry about right now. Or I think I'm not. I don't think I'm even going to be covering Gaussian brackets in this course. So the last thing is both of these have some things in common. We write them in slightly different ways just based on our notation, but this is really saying the same thing. This coefficient, right, which is the probability amplitude, which either way, right, the coefficient, C sub j or C sub q sub j, is the inner product of the state with the definite value of that observable and the state vector, the state function, whichever basis you're in, if you're discrete or continuous. But this inner product has to be the same in all bases, right? And if you actually go back to that last video, you can show that the inner product between, any two vectors you come up with, right? If we have that vector, like the vector psi that we had in the last video, if you did an inner product of, say, white psi in the color basis, or if you did that in the hardness basis, you would actually get the same answer, right? Because it is incredibly important that this inner product is the same in all bases, like we covered in that last video. Lastly, we have, and this sort of goes along with it, that the states are normalized, right? The psi is normalized, where psi inner product with psi, which is psi norm squared, is equal to 1. And that can be, depending on what basis you're in, it could just be, like an inner product with vectors that we'll get more to in Section 5 especially, or that integral definition of the inner product. But no matter which inner product you use, in discrete space, continuous space, just like we showed in the last video, these inner products, they have to be the same no matter what. So hopefully that makes sense. Just a reminder, our normalization coefficient here is, or our normalization condition is that the integral from negative infinity to infinity sine norm squared dx. In a continuous basis, if you're taking the inner product in a continuous basis, this is equal to 1. Want to make sure you remember that. So yeah, I believe that pretty much covers everything. This was just a brief overview of superpositions and working between discrete bases and continuous bases. And in our next video, we are going to start getting to operators.